Okay, part C. Explain in what way this period is related to the orbital period of satellites in low Earth orbits. Okay, so well, my period comes from my force. Now, of course, I'm just having to think through this. Period, we know with simple harmonic motion, of course, it's kind of a projection of circular motion. You've got, a lot of the equations are actually the same. So we know, so if we've got our object going around the Earth like that, and we kind of project it onto the screen here, what we see is simple harmonic motion. Okay, so is that thinking along the right lines? We can certainly include that in our answer. Now, is that period the same as that period?
We can look at the...
We can have a think about that. What do we reckon?
Can we compare the... I don't know if this is along the same lines exactly, but can we compare the Newton's gravitation formula for the and work out a period from there?
Yeah.
And compare it to our formula? Would that...
That's probably a good idea. So, here's our period. Let's keep this one up there. Here's our period there. So let's, I'm going to rub out this and hope I don't need it. Right, so for orbits, so low Earth orbit, I know that my centripetal force is given by the force of gravity. That's what's keeping this thing going in circular motion. So centripetal force equals gravitational force. So that implies that my centripetal force, mv squared over r, and r, I'm talking about this distance here now, maybe we should use big R, at that point there, equals g m over r squared.
I think that's squared, yeah.
Yeah, okay, so we can find what our velocity is, then we know how long that loop is, so we can find how long it takes to go around. So, ends cancel, of course, and we can get rid of one of those r's. So v squared equals g m over r. V equals root g m over r. So our period of orbit is, of course, our distance over our velocity. I guess we should call it speed because
circular motion.
Velocity is changing as it goes around there. Velocity is a vector. So distance over speed. So distance is, of course, 2 pi times our radius. Our speed is root g m over r. So this comes out as 2 pi. Now my r is going to come up as a 3 over 2 over root g times our mass. Right?
Yeah, I think so.
That looks right. It says r times the square root of r, so that goes up. How does that compare? I need to turn my mass into rho.
Yes.
So 2 pi r over 3 over 2 times the square root of g times 4/3 pi r cubed equals, okay, square root of r cubed, that's r to the 3 over 2, we've got r to the 3 over 2 there. Get rid of them, that's good. What have we got? Well, this is almost the row out, isn't it? 4/3 pi r cubed, that's my volume, and it's density times volume. Actually, going back there, once I've got rid of my r to the 3 over 2, this is exactly the same as this one here, isn't it?
It is. Nice one.
So, equals root 3 pi g over rho equals the SHM period. So, they are the same.
There we go.
Who would have thought it?
I started to get a bit worried with some of those R exponents, but it came out in the end. Yep.
Work through it, yeah. Okay, let's just check we've answered the question here. Explain in what way this period is related to the orbital period of satellites in low Earth orbits. So our answer has to have some explanation as to it. So we can say, yes, they are the same, and here's a mathematical explanation of why that is so. I think graphically also we can say that project circular motion, you get simple harmonic motion. I think that's a worthwhile statement to put in the answer as well.
Something like, you might say the circular motion as a reference circle model for the
yeah,
for the simple harmonic motion.
That's a good word to get in. So we could say the low Earth orbit is a reference circle for the simple harmonic motion. Of course it is, yeah, because when the object is there, you know, think about, well, a centripetal force is just the mass of gravity to the centre, the force of gravity to the centre of the Earth. In our tunnel, the force there is the gravity to the centre of the Earth. They're the same. Therefore, the period of that one is going to be the same as the period of that one. It's going to be the same.
Also, as it moves around in its orbit, your radius that you're considering the mass, that you're not considering the mass beyond that radius is changing too. At any individual point, it's always at a full radius, but maybe I should. You might be a little bit off meeting this, but for instance, if this moves around to this location, the vertical radius is still here. So if we're considering that one frame of reference, the force is still proportional to that smaller radius in the same.
It's one of those that when you've got there, it kind of then seems more obvious.
Didn't seem obvious to me at all.
Okay, how are we doing for time? I think that's almost 25 minutes. Got to go.
Yep, a few minutes left.
Okay.